Hi everyone, today we're going to be talking about topic 9.5, free energy and equilibrium. We've been talking for some time about free energy and spontaneity, and all of this relates to equilibrium in some way. As a reminder of some of our equilibrium rules here, if you must remember, at equilibrium, K tells you about the position of that equilibrium. If K is greater than 1, your products are favored. If K is less than 1, your reactants are favored. And as a reminder, K is just equal to the products, concentration of products, over concentration of reactants. Of course, if your products are favored, you're going to have a value that's more than 1. If reactants are favored, you're going to have a value that's less than 1. We can also use K values as an indicator of the free energy of the reaction, and I'll show you in a few slides how you can actually calculate that. So, if K is greater than 1, this means products are favored. Another way to say this is that the forward reaction is thermodynamically favored. Now remember, if something is thermodynamically favored, that essentially means that delta G is less than 0, or in other words, it's negative. So if K is greater than 1, that means that delta G is less than 0. Similarly, if K is less than 1, that means that the reactants are favored. In other words, the reverse reaction is thermodynamically favored. And in other words, delta G, for the case of K is less than 1, is going to be greater than 0 or positive, which basically means the forward direction is not favored. And so delta G will be more than 0, it'll be positive. And of course, if K equals 1, that means that there is no preference for reactants or products, which also means that there is no thermodynamic favorability. And, of course, that means delta G is equal to 0. And I apologize, these are all under standard state, so you should have that little 0 there. And so these rules all govern whether or not something is thermodynamically favorable. And there's a certain equation that you can use to relate K and delta G. And I'm going to show you that right now. So, at equilibrium, remember that just means that you have no change in concentration over time. Delta G naught, or the standard free energy, is equal to minus RT natural log of K. You can also calculate K by doing K is equal to E to the negative delta G naught over RT. And this relationship here is how you can actually equate your equilibrium constant to the free energy of a reaction. Now, there's a few important notes here, and that has to do with the constants. So R, that's our gas constant, if we remember. And on your sheet, you'll have two different gas constants. The one that we're going to specifically use when we're using delta G is 8.314 joules per mole times Kelvin. It's really important that you use this gas constant because then all of the terms will actually make sense. This is the gas constant in relation to energy and not in relation to pressure. T is in Kelvin, or K. So your temperature has to be in Kelvin. You cannot use degrees Celsius. And because of this relationship, there's a few qualitative things that we can do without ever having to calculate anything. when delta G is near 0, that means K will be near 1. In other words, if your free energy is 0 or almost 0, that means that there's no thermodynamic favorability and your products and reactants are going to be similar to each other. As delta G becomes more negative, the forward reaction is more favored. Which means K increases. So the relationship here is that as delta G goes down, K goes up. Therefore, as delta G goes up, K will go down. And so in a way, they are opposites of each other. As delta G goes down, K goes up. As delta G goes up, K goes down. But it means the same thing. If delta G is going down and K goes up, this means forward reaction is favored. As delta G goes up, but K goes down, that means reverse reaction is favored. And so if you have a reaction in which those values are changing, you can see whether or not one reaction or the other is going to be more favorable. Now let's look at this one practice problem here together. We're given this reaction, N2 plus 3H2 makes 2NH3. We're told K is significantly greater than 1, and we're told that delta H is less than 0. So it says the synthesis of NH3 is represented by the equation above. Based on the equilibrium constant K and delta H of the reaction, which of the following can be used to justify that the reaction is thermodynamically favorable at 298 Kelvin? Now, if it's thermodynamically favorable, that means that delta G naught must be less than 0. This has to be true because we're told it's thermodynamically favorable. And so we can look at these here and we can immediately eliminate two answer choices. It cannot be A and it cannot be D because both of these say that delta G is greater than 0. Right? This one says delta G equals minus RT log K, a natural log of K, is greater than 0. That can't be true because it's thermodynamically favored. Delta G must be less than 0. The bottom one says delta G equals delta H minus T delta S, and all of that is greater than 0. And the reasons are because delta H is less than 0 and delta S is less than 0. But that doesn't matter because this here is contrary to that. And so D and A cannot be the answer. So now we're left for answer choices B and C. Now, if we look at our two other choices here, one of them uses the argument of negative RT natural log of K. The other one uses delta H minus T delta S. But if we look here at this reasoning, this here is true, right? Because we're told that delta H is less than 0. But let's look at this. We're not given delta S, but if you remember, if moles of gas decreases, then delta S is less than 0. And if we look here, we go from 4 moles on the left side of the reaction to 2 moles on the right side of the reaction. And so in reality, for this particular reaction that we're given, delta S must be less than 0. It has to be because the number of moles of gas goes down. And so this is not true. And so this is not a good explanation. And so the only explanation that makes sense here is B. Delta G must be less than 0. Because it's thermodynamically favorable in the right direction, that is what we were told, and because K is significantly greater than 1, right? We are told that K is 5.6 times 10 to the 5th, which means that the forward reaction is preferred. If the forward reaction is preferred, delta G must be less than 0, but answer choice C is just not a good explanation because delta S cannot be more than 0. Your entropy is going down, not up. And so that's how you would dissect a problem like this. You got to look at at those two different relationships and just think about which one actually makes the most sense. In this case, the reason why delta G is less than 0 is not because delta S is greater than 0, but because K is significantly greater than 1. We'll go over some more practice problems together, but for now, that's all. Thanks, guys.